In this section, we're going to look at conic sections, in particular, the hyperbola.
In our last section, we saw that a conic section is what we get when we take a mathematical cone, which looks a lot like two ice cream cones stuck together point to point, and we slice. We said that if we slice horizontally, we're going to end up with a circle, and if we slice at a little bit of an angle, we're going to end up with an ellipse. But what happens if we slice vertically? Well, if we slice straight up and down, make a very thin little slice right here, notice that it leaves the cone for a moment. So here, it's actually made up of two pieces, one part from up here and one part from down here. This would wrap around. It would come around the back part of that cone, like that. And same thing this one. This would come down here and then wrap around the back part of that cone. So here you end up with this sort of U shape and this one, which are sort of pointed toward each other. This is another conic section. If we were to take this and pull it out, you would have a two-part result. You would have something that looks like this. It almost looks like a parabola, except you have another part that is facing in the opposite direction. They are symmetric. They do look the same. They have the same size and same shape. They're just facing in opposite directions. This is another conic section, as mentioned in the title of this section. This is called the hyperbola. Okay? So again, this is a conic section, just like the ellipse and the circle. This is another example of a conic section. However, it has its own definition separate from that of the cone. So let's begin with that. Recall that the definition of the ellipse was a set of all points on the plane, the sum of whose distances from two foci is constant. The definition for a hyperbola will be almost exactly the same, except instead of the sum of the distances, we'll want the difference of the distances. So a hyperbola is a set of points, P, in the plane. And again, even though the cone is three-dimensional, the hyperbola itself will be thought of as a two-dimensional object on the xy plane. It is the set of all points on the plane. The difference of whose distances from two fixed points. Which we'll call F1 and F2. And again, just like with the ellipse, these are called the foci. One is called a focus. Multiple of them are called foci, where that distance is constant. The line through the foci crosses the hyperbola at its two vertices. One is called a vertex, plural is vertices. The line segment between the vertices is called the transverse axis. If you take the midpoint halfway between the vertices, or more simply, if you take the midpoint of the transverse axis, that's called the center of the hyperbola. The midpoint of the transverse axis is referred to as the center of the hyperbola. And as they say, a picture is worth 1,000 words. So let's go and take a look at that. Let's say we have a hyperbola. So the two foci will be sort of inside the cups right here. So there'll be, if one of these is facing up, well then the focus will be above, and if one of them is facing down, then the focus will be down here. On the other hand, if you had a hyperbola where the cups sort of face left and right, well then your foci would also be to the left and to the right. So here, this is the focus, and so is this. Here, that would be the focus, and down here, so with that. All right, if you connect the two foci, you're going to have a line. This line is called the transverse axis. Same thing over here. Notice your transverse axis can go up and down, it can go left and right. In later sections, we'll talk about rotations, so they might not go left, right, or up and down. They might go off to an angle. But for now, we're keeping everything either vertical or horizontal. So here, that would be our transverse axis. And then if you take the midpoint halfway between one focus and another along your transverse axis, this is called the center of your hyperbola. And same thing over here, halfway between the two focus, between either focus is going to be your center. Just like that. Here, the two parts of your hyperbola, your cups, as I referred to them earlier, these are called the branches of your hyperbola. So your hyperbola has two branches. Note what your definition states. Your definition states that if you take any point on these hyperbolas, and it doesn't matter which one, so I'm going to go with this one over here. If I take this point, the distance from here to here, let's say I call that D1, and the distance from here to here, let's say I call that D2. If I take the difference between D1 and D2, I'm going to get a number. That same number I would get no matter what point I picked. If I pick this other point over here, say this one right here, I found this one to be my D1, and I found this one to be my D2. Okay, they're from different branches of the hyperbola, and they are on opposite sides of my transverse axis. And one's clearly longer than the other, one's clearly shorter than the other, and so forth. Then none of that matters, though. If you take the difference between these two numbers, that's going to be the same as the difference between these two numbers. And if you pick some other point, over here, or up there, or up there, it doesn't matter. You will always find that the difference between those two distances is the same number. Now, if this definition sounds very much like the ellipse, it's because it is. The difference being that for an ellipse, you would have the word sum here, and where the hyperbola you have a difference of distances. Otherwise, the definition is very much the same. And so the development of the formula will be almost exactly the same. So much so that our results will mirror it down to just a single difference. So here, recall that if you have x minus h squared over a squared plus y minus k squared over b squared is equal to 1. This was an ellipse with center given by h comma k, with a major axis that was 2a units across, or another way to say that was that a was the distance from the center to a vertex. Where b squared was equal to a squared minus c squared, and where c was the distance from the center to a focus. Either one, since everything is symmetric around the center. Well, then it's going to turn out that our hyperbola is going to have a very similar result. If you have x minus h squared over a squared, instead of plus, now we have minus y minus k squared over b squared is equal to 1. That's a hyperbola. The development for this formula will mirror this one exactly in every way, except for you're going to want the differences of d1 and d2. So it'll be d1 minus d2 will equal to 2a, rather than d1 plus d2. Because it's so similar, I'm not going to go through the full development. After all, you can see our development of the equation of the ellipse and simply change all of the appropriate pluses to minuses, and that would give you this result. Here, our center will be at hk. Just like with an ellipse, a is the distance from the center to a vertex, and again, it doesn't matter which one because it's symmetric around the center. You go one way, you'll get to one vertex. You go the other way, you get to another vertex. Here, you're going to have that b squared is equal to, now again, there's going to be a slight difference here. You're going to have, instead of a squared minus c squared, here that'll be c squared minus a squared. Okay? And here, c will again be the distance, just like with the ellipse. C will be the distance from the center to a focus. This will give us a very useful way of remembering these things. They're almost exactly the same. That plus changes to a minus, and here the definition of b squared has these backwards. So now let's take a look at some examples. One thing to note is that our two can have that our hyperbola can have two orientations, one where the branches face up and down, one where the branches move left and right. The difference will simply be a switching of these. If you have x minus h squared minus y minus k squared, that'll be different from y minus k squared minus x minus h squared. If this one appears second versus if this one appears first, you'll have a different result. All right? So note, if you have x squared over a squared minus y squared over b squared equals 1, then that means that your branches will open left and right along the x-axis, like this. On the other hand, if you have y squared over a squared minus x squared over b squared equals to 1, then your branches will open up and down this way. You can either memorize that, or if not, you'll see here in a moment how you, even if you don't remember which orientation it is, you could always figure it out by plugging in values into your results. So let's go ahead and consider some examples of this. Let's begin with the simplest one, where we're simply given an equation and told to graph. All right, so let's go ahead and graph. Let's try y minus 2 quantity squared over 36 minus x plus 1 squared over 49 equals 1. So this is already in the correct form. This is already something squared minus something squared equals 1. So here we don't need to modify our equation. We simply need to pick out the appropriate components. First of all, let's find our center. What number are you subtracting from x? Well, you're subtracting a negative 1. What number are you subtracting from y? You're subtracting a 2. So that means your center, your hk, is equal to negative 1 comma 2. If you don't like saying it that way, you can always ask, what am I plugging in for x to make this part 0? Oh, I'm plugging in negative 1. What am I plugging in for y to make this part 0? Oh, I'm plugging in 2. 2 minus 2 will be 0. Either way, we get negative 1 comma 2 as our center. Okay. Now, here, our a squared is going to be the denominator of the positive term. Notice here, these don't ever switch. The numerator might switch, but the denominator stays the same. So here, a squared is going to be 36, which means a must be 6. So a equals to 6. That's the distance from your center to a vertex. Distance from center to vertex. Okay. Your b squared is going to be the denominator of the negative term. Okay. With an ellipse, switching around doesn't really make any difference because they're both positive, right? This plus this. But with a hyperbola, one is positive, one is negative. So your a will always be the denominator of the positive term. Your b will always be the denominator of the negative term. Okay. So here our b squared is 49, which means our b is just the square root of 49. In other words, 7. Now, in an ellipse, your a told you the distance from the center to the vertex, and then your b told you the distance from the center up and down or left and right along the minor axis. But here our hyperbola doesn't have a minor axis, at least not one that we've mentioned before. So what is that going to give us? All right, well, this is hard to describe in words. We'll see where this number comes in when we actually graph. So this number will be used for something in the graph. It's just something that's not quite as easy to describe as, oh, it's how far the vertex is. But we'll see that here in just a moment. And then, of course, our c, well, note that c squared minus a squared is equal to b squared. C squared minus a squared is equal to b squared, which means that if I add the a squared over this way, I get c squared is equal to a squared plus b squared. Oh, but we know our a squared and our b squared. That's 36 and 49. Which is what, 85? So c squared must equal to 85, or in other words, c is equal to this plus or minus the square root of 85. So from the center, you can get to a focus by going in either direction, plus or minus. You can go square root of 85 units in either direction. All right, so let's go ahead and graph this now. Okay, begin with your center. -1, 2. Now, your A tells you the distance from your center to your vertex. Notice that here you have y in the numerator of your positive term. That means that your hyperbola will open up or down. Okay, so that means that I know that my focus will always be in line with the vertices of my hyperbola. All right, so if they open this way, then the hyperbola has a transverse axis that is horizontal, but if they open this way, it has a transverse axis that's vertical. And that's what we have here. Our y squared is the numerator of the positive term, so we know that our focus will be above or below the center. Okay, so it's going to be 6 units above or below the center. All right, 1, 2, 3, 4, 5, 6. And down, 1, 2, 4, 5, 6. All right, so we have our 2 vertices. All right, so now I said something about B being a little bit difficult to describe. Okay, I know that my hyperbolas will do this. They'll open that way, this way, and this way, right? Because y squared is on top, so that means that the branches have to open up and down. Question is, how wide are these? I mean, it could be like that, or it could be really, really wide like this, or it could be really tall and skinny like this. And I have no way of knowing from the information I have right now. I don't know which of those it is. I don't know how wide that's going to be. Okay, so how do I find that out? That's what B is going to tell us. It's going to tell us how wide to open our hyperbolas. Okay, how does it do that? We're going to start from our center, and we're going to travel B units in a manner perpendicular to our transverse axis. Okay? So we're going to travel 7 units. Here, our transverse axis is vertical, so we're going to travel 7 units horizontal. 1, 2, 3, 4, 5, 6, 7. And 1, 2, 3, 4, 5, 6, 7. Notice these points will not be on your hyperbola. Your hyperbola opens up this way or down this way. It's not like an ellipse. It's not going to do this. These aren't going to come anywhere near those points. So you say, okay, so how do those help me figure anything out about my ellipse? Oh, sorry, about my hyperbola. Here's what we're going to do. We're going to make a box out of these 4 points. Notice that the box has 4 corners. Connect the opposite corners from each other. So here, those 2 corners, go ahead and connect them together with a dotted line. And don't just stop there. Continue on. Same thing over here. Don't just stop at the corners. Continue on. Those lines tell you how wide the hyperbola is. It's going to stretch out to follow those lines. Wait, but we have a word for that. If you think back to college algebra, what do you call lines that your graph will follow but never quite touch? Those are asymptotes. So here, these are going to be asymptotes to your hyperbola. Here's one asymptote, and here's another one. It is sometimes necessary to find the equations of those asymptotes. Other times it's sufficient to just graph them. Here, if you do need to find them, it's fairly simple. After all, it's just the equation of a straight line. The slope is easy to find because all it is going to be how far up or down did you go? Well, that's just going to be your A. And how far left or right did you go? Well, that's just your B, right? Here, you can always just count it off. From here to here, that's going to be up 1, 2, 3, 4, 5, 6. And then right 1, 2, 3, 4, 5, 6, 7. Oh yeah, those are the same numbers we had before. So this is going to have a slope of 6 over 7. and it's going to pass through the point at the center. Notice that the two lines on opposite, when you connect the opposite corners, they pass through the center. That's not an accident. That will always happen. It's going to pass through the point -1, 2. Likewise, this asymptote has a slope of, we're going to go down 6 over 7. So this will have a slope of -6 over 7, and it's going to pass through the point -1, 2. So we can create the equations of these asymptotes fairly simply. Remember the point slope form of a line, y minus y1 equals m times x minus x1. And just plug it in. Y is equal to, take your y value, which is 2, y minus 2 equals m, our slope is 6 over 7, times x minus your x value, x minus a minus 1. Really, that's just plus 1. You can distribute that 6 over 7. So y minus 2 is equal to 6/7 x plus 6/7. And then you can add 2 to both sides to give us our equation. Y is equal to 6 over 7x plus 20 over 7. If you add 2 to 6 over 7, you get 20 over 7. Likewise over here, you can take y minus your y value, which is 2, is equal to your slope times x minus your x value. Minus and minus makes that a plus. Go ahead and distribute your -6 over 7. That gives us -6 over 7x minus 6 over 7. And then go ahead and add your 2 over that way, which gives us y is equal to -6 over 7x plus 8/7. All right? 2 added to the -6/7 will give us 8/7. And those are the equations of our asymptotes. So now we have our center. Right, we found that first. From there, A tells us the location of our vertices. We know that they're going to be up and down because the y is in the numerator of the positive term. If it had been x in the numerator of the positive term, they would have been on these sides right here. So you would have had a hyperbola going this way and this way. But since y is first, it's going to go up and down. The B gave us these values, which even though they're not on the hyperbola, they do give us this box that helps us find our asymptotes. And finally, we can go ahead and graph this by, that's a point on your hyperbola. It's the vertex. You're going to follow along those lines. And same thing up here, you're going to follow along those lines. And of course, our hyperbolas go on forever, but here we just draw the little arrow to show that we run out of room, but they do go on forever. Finally, what about the foci? Well, remember from the center, you're going to go up or down the square root of the square root of 84 units. The square root of 81 is 9, so the square root of 85 is 9 point something, right? 9 point a little bit more. Let's see, square root of 85, 9.2, give or take. So from here, we're going to go up 1, 2, 3, 4, 5, 6. I guess I'm going to run out of room there. Let me go down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and a little bit more. So there's one of your foci. That one is that's -1, 2. The -1 is going to stay the same because you didn't move left or right. Your x value remains the same, but you're going to go down that many steps. So it's going to be -1, 2 minus root 85. The -1 stays the same, but you're going to go down root 85 from 2. And if you go up that many, that's going to be up 1, 2, 3, 4, 5, 6, 7, 8, 9, and a bit. So right about there. And that's going to be your other focus. And that one will be at -1, 2 plus root 85. And there is our graph. All right, go ahead and give this a try. let's go ahead and have you graph x plus 4 squared. Sorry, that's times 16. 16 times x plus 4 squared minus 9 times y plus 3 squared is equal to 144. I remember the standard form of a hyperbola should have this end as a 1, so make sure you take care of that first. And then go ahead and give this a try. Go ahead and graph. You're going to plot your center, your vertices, your foci, and you're going to have your asymptotes. Go ahead and find the equations of the asymptotes as well. Go ahead and pause the video. Take the time that you need. And once you're done, you go ahead and unpause and we can go through it together. All right, so let's begin. First of all, we want to make this equal to 1, so we divide everything by 144. So that's going to be x plus 4 squared over 16 divided by 144. That's the same as 1 over 9. Okay, so that's going to be a 9 down here, which I'll even write as 3 squared. Minus y plus 3 squared over 9 over 144. That's the same as 1 over 16. So that's going to be a 16 down here, which is the same as 4 squared. And that's equal to 1. So right away, we learn a few things. We find that our a is equal to 3. We find that our b is equal to 4. Remember, a is always the denominator of the positive term. B is always the denominator of the negative term. We find that c squared is equal to our a squared plus our b squared, just as we saw over here. C squared minus a squared is equal to b squared. You can always add the a squared over. So a squared plus b squared is equal to c squared, which means that's going to be, well, let's see, your a squared was 9, and your b squared is 16. So that'll give you 25. And if c squared is equal to 25, that means c is equal to plus or minus the root of 5. In other words, plus or minus 5. Okay, so we now our a, our b, and our c, and that should be sufficient to give us a graph. All right, starting with our center. Oh, I guess I should have said that too. Our center, what number are you subtracting from x? You're subtracting a negative 4. What are you subtracting from y? You're subtracting a negative 3. Or if you prefer, you can say, what number do I plug in for x to make that 0? Plug in negative 4. What do you plug in here to make this 0? You plug in negative 3. So either way, you have your center of negative 4, 1, 2, 3, 4, negative 3. There you go. Our a is going to be 3 units. Notice that your x is the numerator of the positive term. So this tells you that your foci will be lined up, your transverse axis will be lined up parallel to the x-axis. Since that's the positive variable, you're going to have this transverse axis parallel to the x-axis. Now you might wonder, what if I don't remember that? Well, the other way to think about this is, notice that you can't plug in x is equal to negative 4. You say, what do you mean? Well, if you plug in x is equal to negative 4 plus 4 is 0. So this whole thing is 0. This is positive because you're squaring it. This is positive because you're squaring it. Positive over a positive is a positive. The negative of a positive is a negative. You can never make that equal to 1. This is negative. It can't equal to 1. So here that means that you can never have x equal to negative 4 on your graph. So that means if x is equal to negative 4, if you take the vertical line where you have x is equal to negative 4, that line will never touch your hyperbola. Because if that line touches your hyperbola, that means that you found a place where x can equal to negative 4. Either negative 4, negative 3, or negative 4, 0, or negative 4, 5, negative 4, negative 20. But it doesn't matter. You can never have that happen. Because if x is equal to negative 4, then this thing is 0. And that's impossible. Oh, so x cannot equal to negative 4. So your hyperbola can never touch this line, which means it cannot open up or down. Because if it opens up or down, it will eventually touch the line, which must mean it opens left and right. So either way, your transverse axis is parallel to the x-axis, which means your hyperbola will open up left and right. Or if you want to think about it that way, oh, since I can never plug in negative 4 here, since I can't make this be 0, then it can't ever touch this line. So either way, it has to open sideways. All right, so let's continue on. Either way, we know which way it's going to open. So A tells us we're going to go 3 units in that direction. Okay, so 1, 2, 3 units in that direction, and 3 units, 1, 2, 3 right here. That's going to be our transverse axis. These are our vertices. So we know our hyperbolas will open this way and this way, right? Okay, but well, how tall will they be, or how skinny will they be? Well, that's what B is going to tell us. Our B tells us that from our center, we're going to go. Well, here we went left and right to find our vertices. So now we need to go up and down to find our box. We're going to go up 1, 2, 3, 4 steps. We're going to go down 1, 2, 3, 4 steps. And we're going to create a box out of those points. Connect the corners of your box. They're going to go through your center. You don't have to make them go through your center. They will, always. They will go through your center. And the opposite corners here will also, again, you don't have to try to make them go through your center. They will. They'll go through your center. And those are your asymptotes. Here we wanted to find what the equations of the asymptotes are. Okay, well, here we go. We know the slope of these. This one will have a slope of, well, from our center, we went up 4 steps and right 3 steps. 4 over 3. So slope is going to be 4 over 3. And this one is going to have the same slope, but it's going to be negative since it's going down. The 2 asymptotes will always have opposite slopes, because that one's going to go down by 4 and right by 3. And if you forgot what those were, you can always just count them off. 1, 2, 3, 4. 1, 2, 3. And it's going to go through the point at the center, which was negative 4, negative 3. So if they go here, through negative 4, negative 3. So you can use the point slope form of your line. Y minus your y value. Well, since the y value is a negative, that's minus a minus, which right, that is plus 3, is equal to your slope times x minus your x value. Well, minus a minus, that's plus 4. You can multiply the 4/3 throughout. It'll give you y plus 3 is equal to 4/3 x plus 16/3. And then you can subtract your 3 from both sides. And that'll give you y is equal to 4/3 x. You're subtracting 3 from 16/3. That'll give you a positive 7/3. Just like that. Same thing with this one. y minus a negative 3, which is y plus 3, is equal to your slope, which is now a negative 4/3, times x minus your x value. Minus a negative 4, that's plus 4. You can distribute that value there, giving you y plus 3 is equal to negative 4/3 x. Positive times the negative, that's negative 16/3. And now if we subtract 3 over this way, that's going to isolate our y and give us negative 4/3 x minus 25/3. And so those are the two equations of our asymptotes. Right? That's not the full answer, but that was part of our answer. These are our asymptotes. Okay. So now we're just about done. We now know the location of a vertex, and here's our other vertex. And we know our hyperbola have to follow the asymptotes this way, this way, this way, and this way. Finally, the last thing is we're going to place our foci. Notice that your foci are going to be 5 units in either direction of your center. And also remember that your foci will line up with the transverse axis, which means in this case left and right. After all, your transverse axis is the line that connects the two vertices. That's the transverse axis. And your focus will be on, your foci will be on either side following that transverse axis. So from here, we're going to take 5 steps in either direction, left or right. 1, 2, 3, 4, 5. Okay, well, that's going to be what? 1 comma negative 3. And then we're going to take 1, 2, 3, 4, 5 units this way, which was what? Negative 9, negative 3. And there we go. 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, okay. I forgot how to count there for a moment. And there we go. There is the graph of our hyperbola, along with the location of its 2 foci and the equations of its 2 asymptotes. Note that sometimes you will have to complete the square first. Just like with an ellipse, you may have to complete the square in your terms to give your hyperbola in a form where you can easily identify its components, the A, the B, and the C. So for our next example, let's talk about, let's graph. Let's take 4x squared minus y squared plus 32x plus 6y plus 39 equals to 0. Notice that here, even though this is not in the standard form of a hyperbola, you still notice x squared minus y squared, which means you're still going to end up with a hyperbola, but we need to complete the square in order to put it in the standard form so we can identify our landmarks, our vertices, and our foci. All right. Let's begin. We're going to do this in 2 stages. Let's begin with completing the square first. Remember, that entails grouping the x terms, the y terms, pushing the constant over, and then completing the square for the x terms, and then completing the square for the y terms. All right. I'm going to ask you to do that as a review of completing the square. Go ahead and pause the video. You don't need to finish the graph just yet. Just go ahead and pause the video and complete the square so that this is written in standard form. Once you have the equation in standard form, go ahead and unpause and we'll go through that part together. Then we'll graph. Go ahead and pause now and give it a try. All right, so to complete the square, we're going to gather our x terms together. That's going to be 4x squared plus 32x, leave a little space there, minus y squared plus 6y. And then let me subtract my 39 over to the other side, because we want our constant over there. Like that. Okay. Next, what I want to do is I want to group these together, and I want to factor out the lead coefficient. Here, that lead coefficient is 4. So if I factor out 4, I get x squared plus 8x. Over here, the lead coefficient is negative 1. You can write negative y as negative 1y. So if I factor out negative 1, that's going to give me y squared, and then that positive is now a negative. Notice negative 1 times y squared is negative y squared. Negative 1 times negative 6y is positive 6y. So that still works out. That still says the same thing as the line above, although it says it a little differently. Right? That's still 4x squared plus 32x minus y squared plus 6y equals negative 39. But now we're going to complete the square. If I take this 8, cut it in half, that'll give me 4. If I then square 4, I get 16, which goes right there. Remember the pattern? Half, then square. But notice that does change my problem. 4x squared was fine, and 32x was already there, but 4 times 16 is 64. I didn't have a 64 before. That's new. So if I've added 64 to one side of my equation, I need to do the same thing on the other side. Over here, complete the square. Half of negative 6 is negative 3. And if I square negative 3, a negative 3 times a negative 3 is a positive 9. But again, negative 1 times y squared is negative y squared. Okay, that was already there. And negative 1 times negative 6y is positive 6y. That's fine, that was already there. But negative 1 times 9 is negative 9. I didn't have a negative 9 before, that's new. Okay, so if I added a negative 1 on this side, I need to add it on this side as well. All right, so there we go. This can now be factored down. X squared plus 8x plus 16, that's x plus 4 times x plus 4. Or more simply, that's x plus 4 squared. Minus 1 times y squared minus 6y plus 9. That factors as y minus 3 times y minus 3. Or more simply, y minus 3 squared is equal, let's see, negative 39 plus 64, that's 25. And then 25 minus 9 is 16. That's almost what I want, except in the standard form, the hyperbola should have a constant of 1 on this side. So let me divide everything by 16. And now I have my standard form. That's going to give me x plus 4 squared over 4 over 16. That's the same as 1 over 4. So my denominator will be a 4, which is the same as saying 2 squared. Minus y minus 3 squared. 1 over 16. Okay, my denominator is a 16, which is the same as saying 4 squared. And here, 16 over 16 is 1. So now I have everything I need. I have that my center is from here. I have my A, I have my B, and once I have my A and my B, I can find my C, because after all, C squared is equal to A squared plus B squared, and then we can graph. So that's the first stage of the problem. We've written it down in standard form. Now the second stage is to finish this off and graph it. So go ahead and give that a try. Go ahead and pause the video and complete the second half. Now that it's written in this form, go ahead and graph. Once you have your results, go ahead and unpause and we can go through it together. All right, so we have our center. That's going to be negative 4, 3. You plug in a negative 4 for x and a 3 for y to make these 0. Negative 4, 3. Our a is going to be the denominator of the positive term. Right? That's a squared. So a must equal to 2. And then b squared is the denominator of the negative term. So 4 squared is b squared. So 4 must be your b. Here, c squared is equal to a squared, which is 4, plus b squared, which is 16. So c squared must equal to 20. If I take the square root of both sides, that gives me c is equal to plus or minus root 20, which is 4 point something. Okay? So this gives us enough information to create our graph now. All right, starting with your center, -4, 3. That's left by 4, up by 3. We have that our transverse axis will be horizontal. It's going to be parallel to the x-axis because x is the variable in the numerator of the positive term. So A is going to be 2 units left or right. So 2 to the right and 2 to the left. B is going to give us 4 units that forms a line perpendicular to this. So we're going to go, let's see, we're going to go up 4 units. From here, 1, 2, 3, 4. And from here down, 1, 2, 3, 4. We can connect those to form a box, which will then give us our asymptotes. Here, if we connect the corners of this rectangle, notice we don't really have to try to make it go through the center of this box. It will every time. If it doesn't, well, then we've really messed up the scale of this drawing, or we've made something very crooked. So by lining up the corners, that will go through the center. Okay. All right, so we now know our asymptotes. We have our vertices are left or right of the center because, again, x is the variable in the numerator of the positive term. So that means that our hyperbola starts from this vertex and follows along the asymptote this way, and same thing on this side, follows up and down along the asymptotes this way. We can find our foci by starting at our center and moving along the transverse axis that many steps. Remember, the transverse axis connect your vertices, so your foci will be left or right of the center, either plus or minus the root of 20. Since that starts off at -4, 3, note that your y value doesn't change, so you're going to have a focus, you're going to travel the square root of 20 units, which is 4 point something, about 4.5, give or take. So you're going to travel 1, 2, 3, 4.5, and the other direction as well, 1, 2, 3, 4.5. So those are our 2 foci. This one will be at, once again, your y value doesn't change here since you never move up or down, so your y value is still 3. So that'll be -4 plus root 20, comma 3. And this one will be -4 minus root 20, comma 3. So we have our graph of our 2 branches along with the locations of our 2 foci. And finally, we can find the equations of our 2 asymptotes. Note that we know the slopes of these. This one over here has a slope of, to get from here down to here, we go down, let's see, what's this? We go down 4 units, right by 2. So -4 over 2, that's just -2. And it's going to go through the center point, which is -4, 3. This other asymptote will have a slope of +2, Right? You're going up by 4 and right by 2. 4 over 2, that's the same as 2 over 1. And that's going to pass through the point negative 4 comma 3. Same point, same center point. We can now find our equation using the point slope form. Y, and we're doing this one first, y minus the y value is equal to your slope times x minus the x value. Minus a minus, we can write that as a plus. Distribute the 2. We get y minus 3 is 2x plus 8. And then add the 3 over this way to give you y equals 2x plus 11. So that's the equation of one of your asymptotes. The other one is almost exactly the same. Y minus 3 equals negative 2 times x plus 4. Your point's the same, just your slope has changed. You can distribute your negative 2 to give you y minus 3 is equal to negative 2x minus 8. And if you add 3 to both sides, you get y equals negative 2x. That should be a minus 5. And that is our result. Negative 2x. And in fact, my graph's actually even good enough. You can see that. It's got a slope of negative 2, and it comes down 1, 2, 3, 4, 5. It crosses at negative 5. This one, if I had kept the graph going up enough, you'd probably see that crossing up at 11. And that's our result. So we have the 2 branches of our hyperbola, our 2 foci, and the 2 asymptotes that help us graph those branches. And that is our result. Okay. Of course, we can go the other way. We can begin with either a picture or a description of a hyperbola, and then use the features that we get from that image or from that description to create an equation for that hyperbola. For example, let's go ahead and find the equation of the hyperbola that has foci (0, -3, and 0, 3), and which has vertices 0, -1, and 0, 1. As with an ellipse, you do not need to have a graph here. However, you may wish to draw a rudimentary sketch to help you organize your thoughts. Again, this is not necessary, but it can often help, especially if you don't know where to get started. Okay, we have 0, -3. Okay, well that's down here. And we have 0, +3. That's up there. We have, and those are going to be our foci. And then we're going to have our vertices at 0, -1, and 0, +1. Well, that actually tells us kind of a lot. First of all, we now know that our transverse axis is vertical. So we know that it's going to have the form y minus k squared over a squared minus x minus h squared over b squared equals to 1. We now know what form it's going to have. Because remember, if your transverse axis is vertical, if it's parallel to the y-axis, the y is the variable of the numerator of the positive term. However, if your transverse axis is horizontal, parallel to the x-axis, then your x would have been here instead of your y. Okay, we know that our hyperbola will look something like this. Okay, well, that means we also know our center. because halfway between your vertices is your center. Or you can also say halfway between the foci. But halfway between 0, 1, and 0, negative 1, or halfway between 0, 3, and 0, negative 3, that's going to be 0, 0. That's your center. So that means that h and k is equal to 0, 0. Okay, so right here, that h and that k are both zeros. Like that. Okay, so now we need to find our a and our b. Okay, well, a is simple enough. It's b that we're going to have to figure out. A we can figure out directly from our graph. After all, a is simply the distance from your center to your vertex. And that's just one step in either direction. A is the distance from the center to your vertex. And again, that's in either direction. So that's going to be one step. So that's going to be 1. The only one we need to figure out is b. Because after all, b is not found directly from either the focus or from the vertex. It would be, now if we had the asymptotes, well then we could figure that out, but we don't have that. Oh, but there's another way to figure that out. After all, we have a relationship between a, b, and c. Here, recall that c squared is equal to a squared plus b squared for a hyperbola. For an ellipse, it's a squared minus b squared. Yeah? But for a hyperbola, it's a squared plus b squared. Okay, well, we know what some of these things are. After all, c is the distance from the center to the focus, which in either direction is going to be 3 steps. So 3 squared is equal to, we know what a is, it's equal to 1. We just found that a moment ago. So that's going to be 9 equals 1 plus b squared. You can subtract the 1 over this way to give you 8 is equal to b squared. And then take the square root of both sides, and b is equal to plus or minus the root of 8. And there we go. We now know what b is. So here that b is plus or minus the root of 8, but notice it's being squared. Well, if you square, that's going to get rid of the plus or the minus, right? Squaring always leads to a plus, and squaring gets rid of the square root, so that'll leave you just an 8. So right here, that result shows you that this right here is just an 8. So your center, 0, 0. Your a, the distance from the center to the vertex, is 1. And then here we can find what your b is so that you can find what your b squared is. Oh, you know what? I just realized right here I could have just stopped one step earlier. B squared is equal to 8. So in the end, you can put all this together. Y minus 0, we can just write that as y squared over 1 squared minus x minus 0, that's just x squared over 8 is equal to 1. And since dividing by 1 doesn't change anything, usually we would just leave that part off. So you can just write that as y squared minus x squared over 8 is equal to 1. And that is an equation of a hyperbola in standard form that has 0, negative 3, and 0, 3 as foci, and 0, negative 1, and 0, 1 as vertices. Note, you don't really need the graphs for these. However, it does come in handy to organize your thoughts. You can visualize this, of course. You can do that without the illustration, but I do see that it does help. So go ahead and give this a try. As the last example for this section, go ahead and find the equation of the hyperbola that has a center negative 2, 1, that has one of its foci, so it has a focus at negative 2 comma 6, and it has a vertex negative 2 comma 4. You don't technically need a graph, but it is often useful to be able to organize your thoughts by sketching even the most rudimentary graph. So go ahead and give this a try. Pause the video, give yourself whatever time you need, and once you have your equation, go ahead and unpause the video and we can finish this one off together. All right, so again, while not fully necessary, it does often help to organize one's thoughts with a rudimentary sketch. All right, we have our center at -2, 1. So -2, 1, there's our center. We have a focus at -2, 6. Let's see, so that will be up here. And we have a vertex at -2, 4. 1, 2, 3, 1, 2, 3, 4. Okay, so if that's a vertex and that's a focus, we know that our hyperbola has to open toward our foci. Okay, so it looks like that. We know that, of course, that a hyperbola is symmetric. So if we know that there's one branch up here, we know there's got to be another one down here. That's up 1, 2, 3 units from here. So that will be down 3 units, 1, 2, 3 units from here. And here our focus is 1, 2, 3, 4, 5 units up from the center. So our focus would also be 1, 2, 3, 4, 5 units down. This already tells us a lot. First of all, our transverse axis is parallel to the y-axis. So just like in our previous example, your transverse axis is parallel to the y-axis. That means your y will be the variable in the numerator of your positive term. So here that's going to be y minus k squared over a squared minus x minus h squared over b squared equals to 1. So that already tells us the orientation. We know our center, that's going to be -2, 1. Okay, so here we can plug in this k is 1. Right, that's your y value. Your h is going to be a -2. Okay, our a, well, our a is the distance from our center to our vertex. And here we counted that off already. The distance from here to here, that's 1, 2, 3 steps. Or of course, if you want to come down this way, that's also 3 steps. We know c is the distance from our center to our focus. Well, that's up 1, 2, 3, 4, 5 steps. Oh, but we don't know our b yet. We know that our a is equal to 3. In fact, here we can plug that in. That's a 3 squared. We know that our c is equal to 5. Oh, but we also know the relationship between a, b, and c. We have that c squared is equal to a squared plus b squared for hyperbola, minus for an ellipse. We can plug those in. 5 squared is equal to 3 squared plus b squared. 5 squared is 25. 3 squared is 9. And here we can subtract the 9 over this way to give us 16 is equal to b squared, which means b would either equal to plus or minus 4. Well, here, b squared was 16. So we can plug in 16 right there. Or if you prefer, you can put 4 squared. It's the same thing. All right, so we can go ahead and clean that up. That's going to be y minus that 1 from the center of our circle, our y-coordinate from the center, squared, over, our a was 3, and we're squaring it to get that denominator, so that's a 9, minus x minus a minus 2, which is plus 2. Right? We're subtracting away that -2 from the center, over our b squared, which we computed to be 16. And of course, that has to equal to 1, as we always have in the standard form of a hyperbola. And that's it. That's the equation of the hyperbola with these features. Sometimes those features are given to you as a list, other times they're given to you as a graph. Either way, as long as you have a few features, you can put them together to find the equation of that hyperbola. And that's it. That brings us to the end of this section and the end of this topic. If anybody has any questions, comments, or problems, please make a note of those and reach out. And I hope everyone has a nice day.